This is the conversation with Sara Seager. She is an astrophysicist and planetary scientist, professor at MIT, author of multiple books including Exoplanets, Exoplanet Atmospheres, and her memoir, The Smallest Lights in the Universe. She is the recipient of the prestigious MacArthur Fellowship and the director of the Venus Morningstar missions that are trying to find life on Venus. In this conversation, we discuss her journey falling in love with the universe. We talk about her work and her research. What are exoplanets? What are the challenges in finding exoplanets? What are the different tools and techniques and technologies we can use in detecting exoplanets? We also talk about biosignatures, exoplanet atmospheres, extraterrestrial life, the Fermi Paradox, and the possibility of finding life on Venus. This is no time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, rate 5 stars in Apple Podcasts. This project takes a lot of my time, money, and effort. So if you'd like to see it continue, please consider making a donation on Patreon or Anchor. You can buy Super Thanks on YouTube. You can leave a gift on Instagram Reels. Or you can join as a member on YouTube. And I've started giving members early access to all of these videos. If not through monetary channels, then do consider sharing these episodes, leaving your likes and comments, all forms of engagement. They really go a long way. For other forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally. And now, it's no time. Arthur C. Clarke had once famously said, 2 possibilities exist. Either we are alone in the universe or we are not, and both are equally terrifying. What probability do you assign to both of these scenarios? And do you have a hunch if one probability or one scenario is more terrifying than the other?
Great question to lead off with. I do think that there has to be life somewhere. If you just think about the sheer numbers of opportunities, there are hundreds of billions of stars in our galaxy, the Milky Way. But you may not know there are hundreds of billions of galaxies. So think about all those stars, and nearly every star has planets. So there's just untold numbers of planets out there. And when we look around our solar system, when we look beyond our solar system, we see the ingredients for life everywhere. So surely that they've come together somewhere else as life. It's a harder question to ask, can we find life or signs of life very near to us where that's accessible today? So I think there's life out there somewhere. What is more scary? I would have to go with being alone.
Why?
Do you ever look up at the night sky, the dark night sky, and you just realize just how small we are and how insignificant? We're all quite self-centered, of course. We have to be to survive. But really, does it really matter when the universe is so big and so vast, and just looking at the night sky, we can't even count how many stars are out there?
So you're going with being alone is more terrifying.
I am.
Okay.
What about you? Would you go with one or the other?
So I agree with Arthur C. Clarke. I find both equally terrifying. I could make the case for either. Right. Yeah, I could steal mine either case. But you're right. There's a certain different kind of terror associated with just being alone in the universe. So,
definitely.
Yeah. I can resonate with that. A lot of things to unpack here. But before we go there, before we dive into your work and your projects, I want to take a digression, talk about your childhood and your journey. You've said in the past that one of your first memories was looking at the moon from your dad's car when he was driving, and the moon seemed to be following you and you were captivated by it. When you were 10, your family went camping in the Bourne Echo Park, and at night you slipped out of your tent and you came across this visual of a sky full of stars. And you've described that moment in your memoir. You've said that your heart stopped and it was your first glimpse of real mystery. Later in life, one of your first jobs was at a carnival, and you used up all your savings from an entire month to buy what every teenager wants to buy, a telescope. And then you spent many chilly nights in a parking lot trying to look up at the sky until you found Jupiter. There's a play called Equus, which is about this boy who has this blinding love of horses. And there's a psychiatrist in that play that's trying to help the boy, who says, a child is born into a world of phenomena, all equal to their power to enslave. It sniffs, it sucks, it strokes its eyes over the whole uncountable range. Suddenly one strikes. Why?
Moments snap together like magnets, forging a chain of shackles. Why? I can trace them. I can, even with time, pull them apart. But why at the start they were ever magnetized at all? Just those particular moments of experience and no others? I don't know. Why do you think these moments in your life were magnetized at all to begin with? Why do you think you were attracted so strongly to the moon, to that sky full of stars? Why did you want to use up your savings to buy a telescope? When you look back now, are you able to trace the source of all that love?
No.
No?
In fact, I do think other lucky people have it as well. And something gets triggered and a seed is planted and one recognizes the true passion. And I'm just really grateful that I got to experience all of that. I do not know why or how it happened. I just know for me the stars aligned, that I was able to get a job doing what I love, and that what I love, I recognized it so young.
It's almost like the way you describe it is like love at first sight. It just clicked.
Love at first sight. It is, but it wasn't always there. I mean, you've condensed, 15, 20 years. I mean, I did have a phase where I was not. Okay, so before I bought the telescope, I'd say fortunately or unfortunately, I was the typical teenager for a while. Was not studious, didn't pay attention to school, and just, went out on the long nights with other teenagers. So it wasn't always there, but it kind of, these punctuated moments, really stuck with me. And looking back, it seems to make perfect sense. I don't know where it comes from. I just really hope that other people can recognize it when they see it.
It's such a magical feeling to be
so
able to
magical.
find.
And I'm telling you, that night will always be with me. I mean, think about it this way. My dad, he was from London. He was the type of person who liked to wear a tie on the weekends.
Right.
And he would not want to go camping. It was just because my parents were divorced, and every summer I spent with my dad, and he would get a babysitter, usually one of his patients. And this patient couldn't believe we had never gone camping. So my dad only had that one night ever that he went camping. And look how lucky I was. A moonless night, a clear sky, a dark sky, not cloudy.
I love such moments that spark off decades of passion and so much work itself. Let's dive into your work. There's a lot to explore. I want to start with a silly question, but I think this simple definition will help set the foundation for everything else to follow. What is an exoplanet?
What is an exoplanet? An exoplanet is a planet that orbits a star other than our sun.
Okay.
Now, all those stars out there are suns. So if our sun has planets like Mercury, Venus, Earth, Mars, Jupiter, etc., it makes sense that other stars have planets also, and they do. And people have wondered about this for literally thousands of years. And for the first time in human history, in the last few decades, we've been able to find and study these exoplanets.
How many exoplanets are out there, both in our galaxy and in the entire universe?
Wow. Well, so far, we can only find planets within our own galaxy so far. And we have several thousand planets.
Okay.
We could each, look up a specific number, but it's changing. So it's changing. But let's say several thousand. And we have several thousand more planets that are planet candidates, but they're not confirmed yet to be actual exoplanets. And we think most stars have planets, more than one. So if you want to know how many planets are out there, there's hundreds of billions of stars in our galaxy alone. And let's imagine that most stars have a handful of planets. We're easily getting to 1 trillion. I mean, it's so big you can't even get your head around it. You hear of billionaires, but you don't hear of trillionaires. It's just such a giant number. It's almost not even worth enumerating because there's just so many.
So there's trillions of planets that we have estimated to...
Right. That's a really important point because so far we are like children, like babies. We can only study our very nearest neighbors. It's like you know that there are billions of people on Earth, but how many will you get to know? How many will you get to know well? Maybe your neighbors or the people in your apartment building. So we're kind of just looking at our neighbors right now. That's what we can do.
And so far we have found 1,000 of them.
Several thousand.
Several thousand of them. But this is not counting exomoons, which I think are harder to detect.
Harder. We have not really had any reliable exomoon detections yet.
Okay.
There are reports, but if you dig deep, they're kind of iffy.
So there could be billions of exoplanets and there could be billions of exomoons as well.
Right.
Increasing the sample space even more.
Exactly. I mean, do you see now why the first question you're like, is there life? I mean, it's not very scientific, but just based on those sheer numbers, no matter how low the probability is, a low probability multiplied by a giant number is still a giant number. So, yeah.
the numbers work in that favor.
Work, right?
In a TED talk, you compared the difficulty of finding exoplanets similar to that of looking for a firefly next to a searchlight that's quite far away. Let's linger on some of the problems. What are these obstacles that are in your way if you're trying to look for exoplanets? What are the challenges that exist that you're trying to solve for?
Right. Well, the main challenge is that any exoplanet is right next to a big, bright, massive star. So like on its own, we could easily find and study planets with our telescopes. But the fact is that the star is so big and massive and bright, it gets in the way. So the challenge is that our techniques have to be able to work within that star being right there. And like what that translates to is that our detection and our characterization techniques, let's just say they have to go to many decimal places. So like if you were going to build a table like this, and let's say this table is 4 feet by 2 feet, and you're going to build it. You're going to go to the store and you're going to buy some wood, but are you going to buy 4.000000 feet or just 4 feet?
Right.
So our techniques, it's laughable. We have to go to like 4 decimal places to 5 decimal places, sometimes to 10 decimal places, depending on the technique. We can't do the 10 decimal place yet. And so our biggest challenge is whatever measurement we need to make, it has to be so incredibly precise. It's pushing the limits of like our detector technology, our computer software, et cetera. So I can give you a more specific example if you'd like, but that's the bottom line.
Let's go for the specific example.
Sure. Well, the specific example is, let me think for a moment. I mean, there's so many examples, but our most common way to find planets right now is the so-called transit technique. So if we imagine that we have a star, well, let's take, it's a rectangular star, and a planet is smaller. The planet orbits the star, like it could be orbiting in the plane of the sky like this, but some of them, they're orbiting in the plane of your viewpoint, and you can see it go in front of the star as seen from your viewpoint. Mm-hmm. We call these transiting planets, as it transits the star every orbit. Well, what happens is we can't spatially resolve the star. We just see the stars like a pinprick of light, but we can watch that light dim by a tiny amount, actually. And so we have a space telescope called TESS, Transiting Exoplanet Survey Satellite. It monitors tens of thousands up to like millions of stars at one time. And our computers look for this tiny drop in brightness that indicates a transiting planet. And these transits, they range anywhere dimming of the star ranges anywhere from 1 part in 100 to 1 part in 10,000 or even smaller. Yeah.
So you mentioned one of the big challenges of detecting exoplanets is because they're next to such a bright star, and the transit technique is one way of detecting exoplanets. You've actually listed down many of the techniques, technology solutions that we can use in your book, Exoplanets, this book that you put together. You've also spoken about direct imaging, coronagraphs, the Starshade Project, radial velocity, microlensing. I'm going to ask you an unfair question. This is going to be the first of many, I'm sure.
Okay. No.
But can you summarize many of these different techniques? We already spoke about the transit technique. Mm-hmm. What are these other techniques and technologies we can use to detect exoplanets?
Yes. Well, we can divide them up into 2 categories, direct and indirect.
Okay.
So transit is indirect because we're not seeing the planet. We're effectively seeing like the shadow of the planet. It's not even really, we're effectively seeing like the shadow the planet is casting on the star. It's not even really that. There's indirect and direct. Indirect is like transit, where we're looking for an effect of the planet on the star. Right. We have one called the wobble method or radial velocity. You know, the planet orbits the star, and the star is also moving due to gravity of the planet. We say the planet and star orbit the common center of mass. So the star is also moving, and we can measure that star wobble, actually. In fact, we're measuring the line of sight motion of the star down to levels of like centimeters per second. We can measure the star's motion along the line of sight to walking speeds. And that's how we can infer the presence of the planet. Indirect. We have gravitational microlensing, indirect. And then we have direct techniques. And those involve blocking out starlight so we can see the planet directly. And that means direct imaging. See, because we're seeing photons directly from the planet. We're getting rid of the star. Now, not everyone will have done this, but being in New York, I know you got a lot of snow this year. Have you ever tried to take a picture of a person in the snow?
Yeah, I guess.
It's really hard because either the person's all dark and the snow's really bright.
Right.
Well, usually that's what happens because our detectors can't handle the dynamic range of the bright snow and like the just dark regular person.
Right.
We have that same problem when we try to look at a star and planet together. The star is so bright, just like the snow, it overwhelms the image. So we literally have to find a way to block out the starlight using various techniques to see the planet directly. And we've done that for very hot, young, massive planets that are really far from the star, that are shining with some of their own energy left over from when they formed.
And what is gravitational microlensing? How can you use that to detect exoplanets?
That is an amazing technique that Einstein first put out there. We don't know if he ever thought it was doable, but the bottom line is that mass bends space.
Mm-hmm.
And so if there is a star, I want you to imagine for a moment that, well, let's do it with the Legos again. Let's say we have a background star, and let's say you're the telescope. The telescope is where you are. And we have a star and planet that you can't see them. They're just dark. They're too dim. But the background star is like a big giant star, so it's very bright. Where the background star is like in the center of near the center of our Milky Way galaxy. Now these lenses go by, mass bend space. So now what's happening is the star that has to be directly lined up. It's just random. They're passing by. Some of the rays from this star, instead of going to outer space, they're getting bent around. The rays wanted to go out there, but we're getting extra light coming our way because it hits that little distortion in space. And then they come towards you. So as this star and its planet go by, you never see them ever. But the background star brightens a little. So for a while, instead of looking like this, it looks like this. It's big. It looks brighter. And by the way it brightens and the shape and the duration, we can pick out planets that are there. Crazy, right?
So cool.
So cool. And we found probably a few dozen exoplanets that way. And later this decade, so around 2027, a new telescope is going to launch, a NASA telescope called Roman. It's actually named after Nancy Grace Roman. And it will be doing a survey, and it will find thousands and thousands of microlens planets.
Wow, it's so cool.
But just one reason why most people haven't heard of microlensing is, when the planet and star, let's see, I lost my planet and star now. When these planet and star go by, you're never going to see them again because we can't see them. They're too dim. They're just brightening the background star. But the chance that they line up with another background star is pretty much zero. So a lot of people haven't heard of it or don't really talk about it because they feel like there's no value if we can never follow it up. But there is value. It's like doing a census. You're going to learn about all the types of planetary systems out there. And in fact, its highest value in my mind is it will tell us how common planetary systems like our solar system are. So far, we have found no solar system copies.
This will just help you detect the planet, but it won't tell you much about the planet itself, or you can use microlensing to actually know some properties of the planet itself.
You can know the planet's mass, and sometimes you can know the planet's mass and something about its orbit, like how far it is from its star.
Let's dive deeper into another technique that's particularly close to you, the Starshade Project.
Starshade. Mm-hmm.
In 1962, Lyman Spitzer had published a paper titled The Beginnings and Future of Space Astronomy, where he proposed this occulting disk in front of a telescope. But for some reason, this idea never gained momentum until you brought it to life again. What is this idea, the concept of the occulting disk in front of the telescope? And then what is the Starshade Project? What is the science and engineering or the design aspects behind it?
Yes. Well, it is my favorite and a favorite way to think about finding another Earth is to send a telescope above the blurring effects of Earth's atmosphere to see the planets directly. But remember, we were talking about the decimal places we have to go to? We would have to block out like a sun-like starlight to 1 part in 10 billion, billion, because our sun is 10 billion times brighter than our Earth is at visible wavelengths. Now, that's not easy. Remember, we're saying if you're going to build a deck or whatever you're going to do, you're not going to be measuring. I don't know if you've ever done anything to 10 decimal places. Never. Okay. I mean, most people why would you? It's just insane. So it's very hard to do. So there's many ways to do it. But one way is to put up a giant screen attached to its own spacecraft. And it's literally just blocking out the light so you can see the starlight, so you can see the planet light directly. Now, imagine for a moment you put up a big spherical screen, like a big circle, and you block out the point of light that is the star. In the end, do you know what happens? You're not blocking out the light because light can act like a wave. And that light waves by, it hits the edges of a giant screen, and it makes ripples in your image. So if you were to put a giant screen in space and work with a space telescope and snap a photo, snap literally an image, you would see ripples like rings of light. It's like dropping a pebble in a pond. You've done that. You see ripples, waves, just waves like that. Now, Starshade is a very special shape. Lyman Spitzer back in the 60s figured out what shape does it have to be, not a giant circle like a disk. It has to be a flower-shaped pattern. And you know what happens? Then the light acts like a wave. It hits the edges of this special pattern and interacts with itself. It would be like dropping a pebble in a pond, but now the pond is perfectly smooth to 1 part in 10 billion. And all the waves are pushed to the outer edges. It's just amazing that he came up with this idea. And you know what? It's just hard to build. So every decade since Lyman Spitzer, it has been revived, actually. And it's an incredible idea. It's been matured by NASA. It's basically ready to go.
What are some of the engineering challenges involved with sending this giant flower-shaped shield into space and then making it completely in sync with this telescope?
Right. Well, in the 2010s, when I took over in 2013, and after my concept study wrapped up, the NASA team asked that question, like in really concrete terms. What are our 5 hardest problems, and solve them? We solved all of them. One of them is the shape. Like, to get to 1 part in 10,000, 1 part in 10 billion, it has to be a very precise shape. And you have to show you can build something in that shape. And that's what the pedal is on my wall. You should get a picture later. It was one of the early Starshade pedals made for demonstrating manufacturing tolerances. If Starshade has to be made to 4 decimal places in its shape, you have to be able to measure that and prove you can do it. So that's one of them. Another one is how to stow and deploy Starshade. Starshade is tens of meters in diameter. And the pedal on my wall is a full-scale pedal. And I have something to show you for a moment here. The Starshade, the 1% scale model.
All right.
Isn't it beautiful?
Looks amazing.
Well, now I want you to imagine this being 100 times bigger. So it's big. And by the way, the shape has to be so precise. Literally, I've had people get, this is so sharp and pointy, you can draw blood. And you know what else? If you have genes, it'll pick up a thread. You know how genes are so hard to destroy? Yeah. And in fact, one of the technology tall poles was the edges have to be so sharp, like sunlight could, our sunlight, not the starlight, but our sunlight could hit this and bounce into the, field of view. So the edges have to be literally like razor sharp to avoid that. Yeah. I'll just give you one more challenge. By the way, that 1% model was used in testing a scaled down version in the desert in Nevada, in Death Valley. And they went over a few kilometers in scale and put Starshade where it was to demonstrate that it can work.
Wow.
Yeah. So the other challenge you mentioned was in space, it has to be lined up almost perfectly, right? Because we have to block out starlight and not block out the planet light. So that is really hard as well. And we do a lot of docking at space station. We've done some formation flying in Earth's orbit. So we just had to show that really far away where Starshade would operate, very far from Earth, there's almost no gravity. And we had to demonstrate that it boils down to a sensing problem. It's a bit technical to explain, but let's just say we demonstrated that we can achieve the formation flying precision necessary. Yeah.
What timelines are we operating on? When does the Starshade project launch? And then which exoplanets are you targeting first?
Good question. Well, we would target the nearest, brightest sun-like stars, and we have a list. We have our favorite list. There's about a dozen stars that are prime for this. And Starshade could come in many sizes and work with many different telescopes. I hate to break this bad news to you right now. Remember, before I said Starshade has been started in the 1960s. It's been revived every decade. Sometimes it's put on the shelf for a while. And unfortunately, NASA has decided right now to not pursue Starshade as their first choice for finding another Earth. But I and some others, we're keeping Starshade alive, so the knowledge is still maintained. And you can go to projectstarshade.com and just follow where we're at whenever you check it out. Yes.
What's the first choice now?
Well, the first choice right now is called a coronagraph. It is a object. It's like a Starshade, kind of, if you want to think about that, but inside the telescope.
Right.
And so the pros of that are you're only launching one thing, one telescope, not a telescope, and secondly, a Starshade. So it seems simpler. The negative of that is that in order to block out the light when something's inside the telescope has to be perfect. And any little defect, light bounces around and mixes up. I just want to give you my analogy for it because we're really excited about our analogy. Let's imagine you have come to my office with a gift of banana bread, let's say.
Okay.
And you bring it to me and tell me the ingredients. Because you know how people are like allergic to everything these days? Isn't everyone like, you go to a restaurant and they have this problem and that problem? Okay.
Yeah.
Let's say I don't eat cinnamon. And I'm like, oh, is there cinnamon in this? And you're like, yes. I'm like, okay, well, I'm going to need you to take all the cinnamon out. Now you have 10 billion parts flour and 1 part in 10 billion. So 10 billion, grains of flour. You have 1 part per 10 billion cinnamon. So it's going to be pretty hard to pick it all out, right? But you probably could if you had to. Yeah. I'm sure you could go around MIT and find like a sophisticated chemical analysis tool and somehow separate it. Okay. We would do our best. Well, let's imagine you let me know in advance. Hey, I'm coming. I'm bringing you this banana bread. And I say, oh, by the way, I don't eat cinnamon. Can you please keep it separated before you mix it together? You'd be like, sure. And you bring the cinnamon and you can put cinnamon on yours. So with Starshade, we separate the light. It's like separating out the cinnamon. We separate the light, the planet light, before it enters the telescope. The chronograph operates with the planet and starlight mixed together. They're all mixed together. And it's like picking out that cinnamon. Now you have to pick out the planet light. It's just a lot harder. It doesn't mean you can't do it. It's just harder. And you think you've saved because you only have the one telescope. You're not doing information flying. You're not doing some of the other complicated things, but you've translated all that complexity into having separated out the planet light at a later stage. And as that mixed light bounces off imperfections, it's really hard to disentangle. So your telescope has to be perfect.
If it has that limitation, then why has NASA picked that as their first choice?
I mean, I think that's a question you have to ask NASA.
I will. That's my next question. And my list of questions, the first one I'm going to ask them.
But there's always trades and there's always back and forth. In astronomy, people have taken pride that every decade in the US, there's a committee that gets assembled to do a priority rank ordered list of what should we do. And indeed, the search for another Earth from space came at number 1. But because everyone has to work together, everybody's got to be on board together. We could have done Starshade with a small telescope. It's so efficient. It's so efficient at observing. It can observe all wavelengths together, unlike the chronograph. And it just turns out that it's so efficient we could have a small telescope. But you know what? For the rest of the astronomers, they don't want a small telescope. They want a big telescope. And the chronograph is easier. People, there's a bit of misinformation out there, but people thought it's easier to put a chronograph with a big telescope than a Starshade with a big telescope. So it kind of, I think, went from there. It went from, it started in the right place. It started in a place that most astronomers want a big telescope. Starshade is better and can get away with a small telescope. So I think there's just a lot of decisions. I'm sure you've worked or people work in large groups and you don't always come up with the optimal solution for each interest. And that's what happened.
I believe you coined the term coronagraph as well with your colleague, David.
Actually, I don't know. I did not. I can tell you where the term coronagraph came from, though, which I'd like to.
Sure.
Have you been lucky enough to see a solar eclipse, a total solar eclipse?
Not a total one, fortunately.
Okay. I want you to try to see anyone listening, a total solar eclipse in the coming years. There's one coming up in Spain, I think in 2026.
Yeah, I think Egypt would also have
Egypt as well, yeah. Egypt. Oh, wow. Imagine seeing that with the pyramids. And the total eclipse, we're not talking about partial here. Yeah. Now, when you see the total eclipse, what is amazing is you're blocking out the sun. Well, the moon is blocking out the sun, and we can see the corona. It sounds like crown. Like the sun has this plasma that's shooting off of it. But when the sun is there, it's so bright, we can't see the corona. When the sun is blocked, we can see the corona. Now, back in the 1920s, a French optical physicist named Leo, he wanted to see the corona anytime. It was very hard to see in a solar eclipse. It has to be nearby. The sky has to be clear. So he invented a device he put inside the telescope. He called it a coronagraph. Yeah. So he can see it anytime. And now we've borrowed that term, the whole community, to call coronagraph something that blocks out starlight, not just our sun's light.
All of this sounds so cool to me.
Yeah.
I think detecting an exoplanet is one challenge in itself. And we've spoken about some of the challenges and the solutions and techniques. But then detecting whether that exoplanet has an Earth-like atmosphere, whether it's conducive to life, is a whole different subject itself.
It is a whole different subject. It is.
You mentioned there are trillions of exoplanets out there, but
how many of them actually harbor life. In order to gauge that number, you've come up with a new version of the famous Drake's equation. You've called it the Seager equation. So let's do another quick definition. What is the Seager equation? What are the different terms? And then what does that tell us about the number of exoplanets that are out there that might have life?
Right. Well, first of all, I want you to know I asked Frank Drake, while he was still alive, if he was okay with it. But of course, I made the change first and then asked. That's kind of the way you want to do things. Yeah. He was like, sure, it's fine. He was so generous. Well, just like the Drake equation, it is not a real equation. It's just a list of terms to illustrate the process. And also like the Drake equation, it's not predictive. So you can't work it all out and be like, okay, there are approximately this many planets with life. It's really just there to showcase what the issues are. And also like the Drake equation, the first few terms we can measure and estimate. And the last few terms we never can. So I have a couple of versions of it. But one term, for example, would be the number of stars in your sample. The next term would be the number of stars that are suited for observation. Like, for example, for transits, remember, the orbit has to be just so. Not all the systems will show that orbit. Another term, for example, is like, are these stars quiet or active? If that matters, are they contamination? Are they very active with spots and flares, which make them not suitable for finding planets? So there's those. And then there's a series of other terms that involve number of planets in the star's habitable zone, or the frequency of that. And then the last two terms are the ones that are the speculative terms that, knobs you can turn. And one of those is, does the planet have life? And another one is, if the planet has life, is it generating a gas that can accumulate and that we can observe from afar? So those last two, the first, what is our sample? We can design a sample with some number of stars, and are they geometrically favorable? We know those. How common are planets in the star's so-called Goldilocks or habitable zone? Yeah. The last few, we'll never know. Those last two, those are the ones we can play around with. So I worked it out for what would it be for the James Webb Space Telescope that is currently operational, and the small red dwarf stars that we can access today. And I just had to tweak a bunch of stuff to get to one. And so basically, half of all planets would have to have life on them. And probably half of those would have to be making a gas that accumulates in the atmosphere that we could see from afar. So it's just kind of illustrating for you that we're barely there. We're kind of excited that we're the first humans with a telescope that can get the job done. But the chances are very low that it'll happen with the James Webb Space Telescope.
What I like about the Seager equation, it's a mix of all the possibilities that exist along with our technological constraints. How many can we observe?
Right.
But when you say that there are some terms that we'll never be able to calculate, do you get the feeling that you might be able to actually refine this window or these intervals for the possible number or the estimates of the number that it might have over time as the technology improves, as we learn more and more about the universe? Maybe we'll start narrowing down on some numbers, or at least a window of possibilities?
Maybe. But I think we need to talk about one other thing before we can answer that. And that is, finding a gas that's a sign of life. It seemed really straightforward. Astronomers have thought of this for nearly 100 years because on our Earth, we have oxygen. We need that to breathe. And we have a lot of oxygen, 20% in our atmosphere. But that without life, without photosynthesis, trees, bacteria, we would have no oxygen. It's so cool that 100 years ago, an astronomer wrote about this in a textbook. And he basically said, we can use oxygen as a sign of life on another planet. Yeah. And what else he did that was so amazing? He looked at Venus with a telescope. He's like, we don't see oxygen on Venus. That's amazing, right? But what has ended up happening was for every gas that could be a sign of life, like oxygen or methane or nitrous oxide, or we have a whole list of them, that let's say I come up with a gas and you're an astronomer or a chemist, you come up with a way that gas can be produced without life. And so we're getting to this point now where we're thinking can we be sure? Or are we just going to have a probability? So that's pretty hard, right? If we wanted to eventually refine everything and be able to say how many planets have life, it's really not clear if we can do that, because right now there's a lot of uncertainty about if we find a gas and can even measure other components of the atmosphere, can we be certain it's made by life, or will there always be an alternate way to make that gas? After all, geophysics, geochemistry, geology, they have the same input gases to work with that life does. So just rearranging molecules, maybe there's always going to be a false positive. I don't know if that's what your thoughts are on that.
Let's go even deeper on that. We have ventured into the world of biosignatures. There's an entire chapter in your book, Exoplanet Atmospheres, called Atmospheric Biosignatures. So I'm going to ask you another unfair question to summarize an entire chapter. What are all these different biosignatures? What are these different types of ideal gases? You've already listed on oxygen as one of them. What are the other ideal gases that make up, I guess, an ideal biosignature? And why do we think they are good markers for the presence of life?
Well, let's first start with gases made by life. It's, you know how we're breathing out gases, like we breathe out carbon dioxide. It's not a good sign of life because we already have carbon dioxide, right? So we have so many gases made by life. I know you live in New York City, but if you can go to the pine forest somewhere and smell all the beautiful smells, biosignatures, gases. And those are other molecules. You wouldn't have heard about them unless you work on plant biology, but like isoprene. They're just, hopefully you're not that person. This happens to me. Something goes really moldy in your fridge, smells really bad. Biosignature gas. Like there are literally so many gases out there. But is there an ideal one? You look so hopeful, but I really don't want to disappoint anyone. I'm not sure if there's an ideal one. Okay, yeah. No, because like, how do you think I feel? I mean, I spent like 15 years on this problem. And if there's no ideal gas, like in science, we're supposed to be accepting of truth, but it's hard. Well, I guess there still are ideal gases, but it's evolving. Like I still think oxygen's an ideal gas. My personal favorite is phosphine. Phosphine is my personal favorite because you asked what are the characteristics we're looking for. Well, first of all, it has to have a spectral feature where there's no other expected background gases. Like carbon dioxide is a very strong absorber, right? And water vapor, those are very strong greenhouse gases. So if your molecule of choice has a spectral feature that overlaps with one of those, you're not going to find it because water and carbon dioxide, assuming they're present, will be dominating. So it has to have a unique signature. Number two, it has to be able to accumulate. You know, sunlight is, you know how people want you to buy something to keep your cell phone clean because it's sending UV light on it?
Yeah.
Yeah. Our sun's UV destroys a lot of molecules. And so a lot of biosignature gases or other trace gases, they're getting destroyed by ultraviolet. So it also has to be a gas that can be produced like in high enough levels to withstand that constant destruction. And then those ones, I think we can handle. We can do calculations and figure out which ones have unique spectra. We can do calculations of UV destruction and find out which ones can accumulate. But it's that third one we've already touched on, false positives. What else can make it that we're kind of a bit stuck on? So we do have to talk about phosphine on Venus. I'm not sure if that's coming or if I should launch into it.
It is coming, but we'll park that aside because I just want to linger on oxygen first.
Sure.
You brought up oxygen. It feels like if I was part of an extraterrestrial civilization and we zoomed in on Earth, would we be certain that there is life on Earth just because there's oxygen? Because it feels like such a reactive gas. In fact, it might convince me that, it's such a reactive gas, there'll just be fires on Earth. There might be no life at all.
Yes. In fact, thank you for mentioning that because I forgot to say, a good biosignature gas is one that is highly reactive because it won't be there unless it's continually produced. But yes, I like what you said. I mean, we used to say, well, hey, if there's an alien civilization with the kind of telescopes we're hoping to build and they're looking at Earth, we used to always say they're just going to think there's life here. You're not from big things like the Great Wall of China, like not from pollution or city lights, but from oxygen because it's so reactive. We used to say that. But now we're not. We're starting to think what you said, that maybe they're looking here and they're being like, there's no way life can be here. Oxygen is too reactive. There are going to be large regional fires at any time. And now, unfortunately, that's our reality. Large regional fires. I mean, it's insane, really. That's exactly why it's so hard, because from one viewpoint, something might look like it's a sign of life, but there can easily be an opposing, very logical viewpoint where it's the opposite. So I don't know that we're always going to be this uncertain, but there's a lot of research here now. There's a lot of activity in the community trying to sort through these problems.
So if you take that Terra-centric view that we need oxygen and water vapor and look for another exoplanet, it's possible we find an exoplanet with oxygen out there, but that's actually true that it might just be so reactive that you might never find life there.
Maybe, but I don't know. I'm still going to stick with oxygen. It's not always a black and white, purely scientific thing.
Okay.
I like oxygen.
Let's go into phosphine. Your personal favorite, your number one contender so far.
Number one, yeah.
I think finding phosphine on Venus is one of the big reasons why you pivoted into working on the Venus Morningstar mission. So what are the Venus Morningstar missions? Why is the finding of phosphine so exciting? And why do you think that might be a marker of the presence of life there?
Right. Well, phosphine on Earth, again, let's just allow ourselves to be terracentric for a moment.
Okay.
Phosphine on Earth, it is only produced by life. I mean, well, maybe there's one or two exceptions, but it produces like negligible, like almost nothing. So phosphine on Earth, it is made by us humans as insecticides and pesticides. Phosphine appears to be made by bacteria in oxygen-free environments like wetlands and other places. And so it has unique spectral features. It can kind of reasonably accumulate in atmospheres. It is still pretty reactive. Yeah, so phosphine, my team, we were working through we were searching for the ideal biosignature gas. And phosphine popped out right away, and we wrote a bunch of papers on it. And we discovered that someone else was working on phosphine as a sign of life, unrelated to us. And it's such an obscure gas. I mean, most people have never heard of phosphine. It's a phosphorus atom attached to 3 hydrogen atoms. And in fact, we have phosphorus on Earth. It's part of our DNA, but it's usually attached to oxygen because we have so many oxygen atoms here called phosphates. So someone connected our two teams. And the other person was Professor Jane Greaves, purposely searching for signs of life on Venus by way of phosphine gas, because she's a radio astronomer and phosphine has a radio signature. So she invited us to join her team. That was pretty exciting. Let's cut a long story short and say in the fall of 2020, we reported the detection of tiny amounts of parts per billion by volume of phosphine in the Venus atmosphere. And the reason I'm looking like this is it was not a hit. It was a extremely controversial discovery. And to this day, it is highly controversial. And so there's 3 reasons for that. And these are the same questions we would have to ask about any future exoplanet discovery. Is the signal real? I mean, these are tiny signals we're looking for, right? Like think about trace gases or noisy data. And some astronomers have not recovered the signal in the data. The data is all public. Some astronomers have recovered the signal, and that leads to the second question. If the signal is real, like we found a signal, did we attribute it to the right gas? Is it phosphine or could it be another gas? And then one other contender is sulfur dioxide, which we know exists on Venus. Now let's assume those first 2 are correct. The signal is real. It's attributed phosphine is the right gas. Let's say we believe those 2 things. Then we have to ask, is phosphine made by a non-life process? And our team wrote 100 pages explaining why it can't be made by a non-life process. But, I don't know. I don't want to say quantity is not quality, but there could be something we overlooked, and we certainly leave room for that possibility. There could be other chemistry we don't know about yet, but it would be pretty hard. So those are the reasons why it's remained incredibly controversial. But for me personally, this was like a career crisis. Right, think about this for a moment. Spent a lot of years trying to find the ideal biosignature gas.
It's right next door.
It's right next door, and no one believes it for a lot of reasons.
Yeah.
So let's think about that for a moment. Now think about a distant exoplanet. Noisy data. Is the signal real? Is it attributed to the right gas? Is it made by something other than life on what's essentially just a dot in the sky? Like, how am I going to continue to invest whatever 15, 20 years I've got left as a researcher when people may never believe it? It's like you don't know whether to laugh or cry because it's so absurd.
I don't know why this ranks on the giggle factor.
I don't know if it does, but it's pretty depressing, I'll tell you that. So in order to figure out what I was going to do with that thought, I took some time away from exoplanets and decided to leverage this phosphine opportunity into asking the question, can we go to Venus? Can we send space missions to Venus and search for signs of life or life itself directly in the atmosphere? And that's how the Morningstar missions to Venus, an international consortium that I started and run, came to be. Now, wait, one more thing though. We used to call ourselves Venus Life Finder missions. But did you know there was so much pushback? Like, which one do you like better? Venus Life Finder missions or Morningstar missions to Venus?
Why is there so much pushback in the community towards the presence of life? Another professor in the Cambridge area, Avi Loeb as well, has spoken extensively about Oumuamua as well.
Right.
And it feels like the number one, the gut reaction to all of these findings has always been very negative.
Yeah, very
in
negative.
general, why is the community against finding life?
So we've been actually, in my work, believe it or not, we've been convincing people to believe, actually. Not that there is life, but that there could be, because we're doing repeatable experiments. Now for Avi, for Oumuamua, that thing's gone. They can't do any more experiments on it, but they can hope to find other cases like it, right? So I do have an advantage in this area. So why people don't believe, I mean, you only need to Google sulfuric acid and sugar, because our DNA has a sugar molecule in it. And sulfuric acid and sugar, it is not pretty. It's like, whoosh, it is insane. You have to look that up later. And so there's reasons why our life, like on Venus, the surface is too hot for life. But just like on Earth, when you go in an airplane or you go higher and higher on a mountain, it gets colder and colder. So on Venus, we're not talking about life at the surface. We're talking about life in the clouds of Venus. Well, the clouds of Venus are not made of water. They're made of concentrated sulfuric acid. So, I can tell by your expression, like almost how old you are, because there's a generation that knows exactly what sulfuric acid is. And that's the older generation. Because remember how it seems like there were no rules in the old days, right? There were no car seats, there were no seat belts, there were no limits.
Yeah.
And when I talk to older people, they're like, yeah, I use that in the basement for like my chemistry set. It's like, what? Like you can't buy that stuff. I mean, it's so dangerous, sulfuric acid, right? So why do people not believe there's life in the Venus atmosphere? Because concentrated sulfuric acid is a nasty, deadly, toxic chemical to all of our life. We use it to clean electronics. Like here at MIT, one of my students found some other student who said, hey, you should go to MIT Nano Lab. They use sulfuric acid. Maybe they have some lab space you could get. I have my own lab now, but when I was trying to get some labs, and you know what? They have these giant vats of sulfuric acid to clean things, to kill life. So that, was like a 30-second meeting because we got there and realized there's no possible way it's relevant. But we still got a tour of the MIT Nano. So that's why people can't believe it, because it's so ludicrous. But what we've been doing is tied to the missions and tried to motivating the missions. I have a chemistry lab here at MIT, and we put molecules in concentrated sulfuric acid. So our DNA doesn't survive. But here's the thing, part of our DNA does survive. The latter part of when you think about the double helix, there's a ladder, and we have adenine, guanine, cytosine, like ACGT, those survive. They get protonated, they get, a little bit altered by the acid, but the ring is there, the whole structure it lasts for more than a year. We put our amino acids. Most people know what amino acids are because they make up protein. Some people who are into bodybuilding, how you have to eat a lot of protein to gain muscle? Some people buy amino acids and eat them. So people know what they are. So we put our amino acids, remember the component of protein, in concentrated sulfuric acid. And guess what? Stable. With one exception, stable. They're half are chemically modified, but they are stable. We've been experimenting with small proteins and with fatty acids. And sure, there's a lot of chemicals that are not stable, but there's this growing list. It's the tip of the iceberg of chemicals that are stable. So now when I talk about all this chemistry, I go to a different university or I meet some other scientists. They can't deny this. These are repeatable experiments. But then we have to go to the next level. Now we need an energy storage molecule because you need it. We eat food, but we store energy and then we release energy. So, it's complicated, but just let's say these laboratory experiments are to motivate the missions. Because if I can come back to you and say, hey, our DNA is unstable, but we have made a DNA-like molecule, swapping out unstable parts of our DNA for stable parts. If I can show you a kind of similar thing to DNA, an informational storage molecule, I hope you'll be sold.
I'm already sold.
Okay. All right. Thanks.
Can you paint the picture for me? If life is creating these signatures on Venus, then what does life on Venus look like? Is it just on a microbe, or is it on a molecular level? Can we see it with the naked eye? Can you paint the picture for me what extraterrestrial life looks like?
Well, if there is life on Venus, we think it is very simple life. Not only is it like microscopic life, like just single cell, but perhaps even more primitive than anything here on Earth. Maybe it's something like how our life started. Like if you ever were to learn about biology, so I've been learning biology because I'm trained as a physicist and astronomer. it's crazy. Like a cell wall is so complicated. Think of it like a tapestry of like so many different threads of different thickness and color and texture. But you can think of the simplest cell that maybe we started with. Maybe it's just like three threads of different texture. It's not like so many. So we think, that's my personal opinion, is that on Venus, it would be the simplest life we could imagine. You know, in our cells, there's helper molecules to transport material. But I imagine these early cells, or on Venus, it just macromolecules can flow in and out through the membrane. You know, it has to be a much simpler system. So it's not only microbial life, but something far simpler than Earth's life because it's nutrient limited and there's just not a lot going on there. It's just like life. We know some people like this, unfortunately. They're barely eking out an existence, right? It's like that.
It reminds me of this visual I came across in Carl Sagan's book, Cosmos, in which he had tried to envision life on Jupiter. And it was also life that would exist only in the atmosphere. There's no surface. And he had created these diagrams, illustrations of these things called floaters that were
I remember
rising.
that.
Yeah. And I was so blown over by that visual. It just reminds me of that. So I'm not completely, I mean, it's not the first time hearing of life existing on the atmosphere,
and I did forget to mention that Carl Sagan first put the idea forward.
Right.
It seemed like when he postulated life on Jupiter, he was just asking what planet could have life. But at the time, we don't think he knew the clouds were made of sulfuric acid at the time.
What would be the philosophical implication of finding life? What happens on day 2? Let's say you find this microbial life or a very microscopic life on Venus. Would that change our worldview in any way? Does that change your daily life? Would that change your perspective in any way?
It's not going to change our daily life, but when we want to take a moment to be philosophical and re-ask that question, are we alone? Wow, we're so much closer to understanding we are not alone. Because if there's life in one other place that has arisen on its own, independently from Earth life, there's just a single other example, it really means it's easy for life to form and evolve. So that would be awesome. If we know that there is an independent origin of life, there has to be life in so many places.
If I can play devil's advocate to that stance,
sure.
Nick Bostrom has said it won't be awesome if we find life because he said, and he used the example of Mars because Mars is the sibling that gets more attention. But he said that if we find life on Mars, that's really bad news because that means you have to update our priors for life existing from 1 out of trillions of planets out there, all the way down to 2 out of 8 or 9 planets in our own solar system, depending on how you feel about Pluto. And that's a massive downgrade of probability, thereby implying that because we haven't seen life anywhere else, there's a great filter that's ahead of us rather than behind us.
I hate that. Yeah.
You hate it?
Well, I hate that in what it might mean for us.
Right.
Like, I think it's fair to say today we're imperiled. I mean, we have been for the last, I don't even know how long. Since World War I, maybe. I mean, certainly since the Cold War. And discovering nuclear weapons, we've been worried about destroying our very existence here. We're clearly, I mean, we are destroying our planet. There's no question. We have overpopulation. But what I like to think, it doesn't help me and you, right? You know, the cockroaches will survive. Have you ever had cockroaches? You can't get rid of them. If your house is really clean, they just need like the tiniest bit of water and they will last like forever. Yeah. Yeah. So, you know, we'll have some life, but we may not have intelligent life. And I think that's where it's going, right? Once we're overpopulated, we're fighting for resources. We have so many wars. I mean, everyone's really worried right now about this.
So there's merit to that argument that if we actually find life on Venus or Mars, that implies that the Great Filter was not before us. That it wasn't like a rare Earth hypothesis that is probably debunked. And then it implies that the Great Filter is ahead of us.
Well, there's merit to the life, but it also depends on your stance on evolution, right? And I'm not an evolutionary biologist, but I do always wonder about this. Like, is intelligence the definitive endgame for evolution? Like, let's imagine there is life on Venus. I will put to you that it could not evolve to be intelligent because it's so nutrient limited. And maybe the droplets, the habitats are small and there's just not a lot of what it needs. Although Yaroslav, one of the postdocs in my group, we together with a science fiction writer wrote a really interesting science fiction. You can look it up. It's called Etchings. And it postulates that on a Venus-like planet, there is a sort of swarm mentality to the life, and it does have some level of intelligence, actually. I know, but it's science fiction. But let's just say there is a lot of life out there, but for whatever reason, it's not intelligent. And then it can't contact us, right? So I don't know. I mean, I don't know what your thinking is on this, but it's a tricky one.
What is the leap that you make from finding a planet with a biosignature and then determining whether it has life? The Miller-Urey experiment suggests that organic molecules are just a natural consequence of having, let's go back to Earth-like planets, Earth-like atmospheres. If you simulate that Earth-like atmosphere in a test tube, run an electric spark through it, the next thing that develops is organic molecules. It's just a consequence of it. Do you harbor the same level of optimism that if we actually find Earth-like planets, it's very likely that there's actually life there?
Well, you're putting me into a bit of a corner here because I want to believe. I don't know if you've ever watched X-Files. You should. It's a series from like I want to say the 80s or 90s. It's really good. And they have this poster, like the start, there's like a UFO and it says, "I want to believe."
Right.
So that's not, this is tricky because we're just, from the scientific viewpoint, I have no answer to that question right now. But to speculate, which of course that's what we're here for, I'd like to think, yes, I want to believe that any habitable world, a planet with liquid of any kind and with energy like coming from its star and with the right temperature for complex molecules, I want to believe that any planet like that will have life. Yes, I want to believe, but do I have evidence? No, I do not. And that's the biosignature gas idea, was that you have to have a gas that won't be there unless it's continually produced, and that if there's no way to continually produce it other than life, it's a sign of life. It's not going to guarantee there's life, but that's why this like growing number of people. I mean, if you interviewed all the young people wanting to work in astronomy, a large fraction of them want to find life, signs of life. So we've really bought into this, and it's going to be, we've talked about it, it's a long haul.
I like that you want to believe and you've kept that dreamer alive. There's a poem by Walt Whitman, I think, about the learned astronomer, about how the numbers you can get lost in the numbers,
right.
But you actually need to keep the dream and let it fuel you. So I completely agree. While we're talking about biosignatures, what techniques, tools, technologies can you use to actually detect the atmosphere, conduct this process that you have called creatively exoplanet atmosphere retrieval? What type of techniques can you use to actually detect the atmospheres of these planets?
Mm-hmm. Well, there are two separate things, and one is detecting it with telescopes. Typically, space telescopes do a better job because our own Earth has gases in the atmosphere that create confusion, and to get above the blurring effects of Earth's atmosphere. You know how turbulence, like on the plane, you feel a bit of turbulence? That's so bad. Twinkling stars, that's because the atmosphere is messing everything up. So we want to be above the atmosphere and make measurements. Spectra, we call it, splitting up light into its constituent colors and looking for pieces of those colors that are missing by gases that are absorbing in special patterns. That's one thing, but retrieval, as it's called, is an interpretation tool, right? Because we can get the data, but we have to make an interpretation of it. And that's more tricky because let me think of how to explain it. There's a word we have like ambiguous, like you can say in the future, let's say today, we can detect water vapor on an exoplanet, but unfortunately we can't tell you exactly how much there is. Do you know how you can have like a humidity sensor in your room? And you can be like, oh, it's 80% humidity. Or if it rains, it's closer to 100% humidity. Or sometimes it's so dry. Have you ever noticed they're so dry and like you look at the reading, it's like 30% humidity, you know? Well, we can't do that for you. We could be like, hey, we have this much water vapor. Let's say we have 1 part per 1,000 water vapor plus or minus 4 parts per water vapor. Like we're not certain how much there is. So we have to have statistical tools to evaluate like what is in the atmosphere and how much it is there. And that's what we just called retrieval. It's like retrieving the parameters you care about from data using complex statistical methods.
And then the believer in us, the moment we find a good biosignature, I'm saying there's going to be life there. We took this digression. We were talking about, the grid filter. And I want to tie that back with the Seager equation. Enrico Fermi went through similar calculations as well at lunchtime. And he landed on the conclusion that there has to be a lot of life out there. But then he exclaimed popularly, where are they? Which came to be known as the Fermi Paradox. What do you think explains the Fermi Paradox? Why haven't we seen any signs of intelligent life if the numbers are so heavily in that, skewed in that favor?
Well, I have my favorite reason, and I'm sure there's a lot of great reasons out there. My favorite reason, it's like the ant theory. Like you have ants, I'm sure I don't know where, well, here we always
We
get
deal with rats in New York City.
rats. Yeah, I was remembering those rats for a moment. My mind definitely went to the rats. I think rats are probably fairly intelligent, actually. One time I was in New York City with my husband and dog, and we stayed in an apartment. I was visiting NYU, and they gave us like this apartment we could stay in for a few days. We drove down there. I was just thinking that after one night out, my husband had to take the dog for his walk at night, and the dog was like in heaven because not only was there a ton of trash, but there were rats, untold numbers, like going back and forth from the trash to their living space. Yeah. And the dog was just, oh my gosh, like the best thing ever for a dog. Yeah, I was thinking about those rats. But here we have ants, and in the spring, for some reason, I don't know why they're coming in the spring, but they come into your house and they kind of do reconnaissance. So if you had like a little piece of cat food, a few ants find it, and then you get the army coming. And eventually they move back outside because I guess there's stuff for them to eat outside. Well, let me ask you this. You can mess with the ants. You can clean off their path and they get confused for a while because their trail is gone. But can you talk to those ants? Like, could you describe your journey from New York City to Boston today? Like, well, we can't communicate with them. They're just communicating through pheromones. Like they're sending chemicals to each other. And that's my favorite theory, that we're the ants, and that the more sophisticated, intelligent beings out there, like, would they talk to us? Could they talk to us? Would they bother?
As an extension of this theory, then, if there are these civilizations that have a million-year head start in terms of technology and intellectual capabilities, that has given rise to the simulation hypothesis that then the numbers are in the favor that they have already been here. And then the world as we see it is nothing but an illusion. This is a simulation. Well,
yeah, I don't buy into that one. But I do like the idea that human life could be short-lived, cosmically speaking. I do love that idea that we may evolve. Like, we live in an incredible time, right, with AI. Have you been watching the latest? It's just, in a way, terrifying. And I think there's this one thought. It's a bit romantic, and at the same time, it's sort of like a romance and also like a horror film, right? That we evolve and we meld with machines, right? And that someday we're no longer here in human form. So it's not so much that I want to think like the aliens have been here in the past and set up our life, but that we'll evolve, like you said, if we had those millennia or a billion years, like who are we? What are we going to be? We're going to be something like so different, right? Maybe we're just swarms of computers surrounding our sun to get energy. There's a popular idea there, like the Dyson spheres, like we need energy and we're not humans. And how would those things, why would they, like, think about AI today, like all these large language models, ChatGPT, Grok, and all that. And imagine if we meld, it can print things, and we've got our intelligence melded with theirs, and we're just hardware now. Now what? Would you bother talking to lowly humans? I mean, no, you don't need them. Yeah.
Yeah, but in a way, I plus my phone is already like a collective consciousness.
Totally.
For that,
oh my gosh,
far significantly amplified than I would have existed just without my phone.
I know, right? And it's younger generation, even younger than you. They're like growing up with this, right? Like even my kids didn't. Well, I guess when my kids got their first phone, it was a smartphone. Unfortunately, it was. Well, you know what? Just like on that thread, it's scary today what kids have. But mine were age 6 and 8 before they even watched TV. I really held off. It was a lot of work, actually.
That's right.
Well, they had these trains they loved. There's this thing called Thomas the Tank Engine. It's so popular. Do you know what that is? Yeah. It's so fun, right? We literally had every train. When you're really little, you can't even put the pieces together, but they would watch, they had the books, and later they watched the movie when they were allowed to, but they got the books, and like, it was like a whole thing. We just had trains everywhere all the time. But, you have to have something to fixate on. But but it's true. Like, we rely on our phones. We have like a culture with our phone, with other people. And where's that heading? Those are brand new, right? We don't even have like a full generation who grew up using that. Yeah, exactly. And then we have other things are starting to happen, like people who are paralyzed are trying to do brain implants. Like, so we're sort of slowly, like, I mean, I don't know what kind of world it's going to be, but when we think about finding signs of life, maybe there's the primitive life, like on Venus, barely getting by, but it's there. And then maybe there's the full evolution to post-biological intelligence where it's something else.
It's so intriguing. looks can be deceiving, Professor. I've seen a life where there was no internet. I've grown up in a house without the TV and the computer.
Great. I'm so excited about that. I'd love to talk more about that. I mean, I have no idea how old you are, like where you grew up, but no, I think it's so important. Like, do you remember being bored, or like being bored is like so important, it turns out. But today's kids, I just don't think they're ever bored.
We had a lot of books, and somehow I think just because you're never aware of the concept of the internet or video games, you just like filled up the time with everything else. So you went out to play, you had books.
Yeah, it's true.
I remember my lifestyle changing completely when the computer and the internet came into my house. So yeah, I completely remember that. Let's look towards the future. While we're talking about these sophisticated civilizations, for your 40th birthday, you had hosted a symposium called The Next 40 Years of Exoplanets. I want to conduct a similar experiment today. I'm going to look 40 years into the future. Let's assume it's 2065. What do you think? How many exoplanets will we have identified that have Earth-like atmospheres by then? And do you think we might have found life out there by 2065?
Okay. So by 2065, assuming everything goes to plan, I mean, unfortunately, these giant space telescopes, like the James Webb Space Telescope, like the big one that NASA wants to put the coronagraph in, I don't know if you know this, but they're usually 30 years from concept to launch. So if it's just been conceived a few years ago, that's still 30 years away. So that thing should have launched by 40 years. Found some true Earth twins, an Earth-sized planet in an Earth-like orbit about a sun-like star, found oxygen and water. So I'm going to have to believe, that is going to happen. We are going to have a couple dozen of these. I mean, that would be the dream. That is the plan. Now, as to signs of life, because of everything we've talked about until now, oh my gosh, that you're going to have a sign of life idea, and I'm going to say, no, here's a way it can be produced without life, and vice versa. It's going to be tricky to know for sure. So I'm going to put my money on the solar system for actual finding life beyond Earth. Venus atmosphere, we can go there, we can rule it out or rule it in. Mars subsurface, so many of us, we just like love this idea that there could be these pockets beneath the surface of Mars with life. So I'm going to have to place the bet on the solar system. Somewhere in the solar system we're going to get to within 40 years, and we're going to have a sample return and literally see that life somehow with some of our sophisticated Earth-based laboratories.
We'll have a definitive answer that they're
possibly... But obviously I have to be as optimistic as possible, okay? If you really pushed me and I had to bet everything I own, but if you wanted me to be as optimistic as I could and things are done right, and we all buy into the new space world where things are smaller and cheaper, and we can focus our efforts and not have to have large community projects like where everyone has to get together. And remember we talked about if we have to build the thing that's optimal for an entire group rather than optimal for a certain goal, it's not happening. But if we can break free and just have very focused missions to find life and sample returns, we can do it.
Let's indulge in another thought experiment. Let's say you have unlimited funding. You're already working on the Venus Morningstar missions. What are the other top 5 contenders, exoplanets that you want to send missions to?
And can I have unlimited number of missions?
Let's do 5.
5, all right. Well, the first thing I would do is go to Venus with, the series of missions. I would want to do a balloon mission with a mass spectrometer to find those complex molecules, not just amino acids. Like you said, those can be made from Miller-Urey experiment, but more complex ones, complex enough to be like a DNA-like molecule. I would send another mission that would be a parachute. Think about confetti. Only the confetti are advanced miniature detectors. They're like a puzzle piece that if they latch onto the molecule that you're looking for, it kind of sends you a signal, yes, no. And there's a lot of them being developed. I'd send that mission. And then I would do, I'm going to use up, 3 of my ideas here. The third one would be a sample return. Really hard to do. Grab some of that atmosphere and clouds and bring it back to Earth. Imagine if you could get a bit of that and put it on your mantelpiece. This liquid, this is clouds from Venus. I know. And look for life. I would want to do those. But each of those builds on the last. So if you find nothing with the balloon mission and the mass spectrometer, if all you find are amino acids, you don't bother doing the next one. As far as my next 2, I would put one on Starshade. The most efficient way to study atmospheres of a good number of the very nearest sun-like stars, to search for planets and study their atmospheres. And again, finding something with any sign. The next mission I would do, that's my number 5, is called Solar Gravitational Lens Telescope. This would be sending a telescope 500 times the Earth-Sun distance. So we'd have to slingshot around the sun, and even traveling very fast, it would still take a couple decades to get there. So we can still do all of this in 40 years. 40, it'll take us like, say, 15 years to build it and then 20 years for it to get to its destination. So what that would do, remember we talked about how mass bends space. Our sun bends space. And if we can also block out the sun, and we know where the planet is, so we've chosen this, we've already found the system with Starshade, we know it's a good system, we line it up, send the spacecraft there, we can then look at the planet in a lot of detail. We can spatially resolve the surface to like 10 square kilometers. So those are my 5 missions, 3 on Venus, 2 on the exo-Earth.
What are other contenders for exoplanets that you want to send missions to?
Well, one thing we had not talked about yet is that, well, exoplanets are so far away, we can't get there yet. I mean, there's talk of how we could send little tiny probes to Alpha Centauri, our nearest star system. But this solar gravitational lens telescope idea, we just be magnifying them. So we're not going to go there, but it's like a step between having the Hubble or the James Webb Space Telescope and actually going there.
So what planets would there be? Do you have any names?
Well, there are, but for now, we haven't found any true Earth twins. They're just beyond our reach, actually, because our sun is so massive and big and bright compared to Earth. Instead, all of our efforts so far have been successful studying small stars because it's smaller, it's not as big, it's not as bright, and it's been easier to find planets there. But these are more like the Earth cousin than the Earth twin. Like the way I like to say it is, let's imagine you go on 23andMe. Maybe you've done this. And actually 23andMe, they're going bankrupt, so you've got to delete all your data. Yeah, don't do that one. But imagine you go on one of these and you find a new relative, a cousin that, wow, this happened to me. Yes, I have a cousin that like nobody knew who it was, and I got to meet her, yeah. It turned out my grandfather, he's not alive. He had an affair, and no one knew about this person. Yeah, it's amazing. She's my half-aunt, and she looks just like my grandfather. Yeah, it happens, very common. So imagine you go on there, you have a cousin, a different generation, they live in a different country. In this case, the person lives in the UK, so speaks the same language. You could have that, and that's cool. It's exciting. But imagine now, and that's the Earth cousin, the planet around the small star. It's not like ours, but it's related. Now imagine you go on one of these 23andMe type things, Ancestry maybe, and you don't find a cousin, you find an identical twin. Like, how does that feel? I mean, it's just mind-blowing. That's what we want to do. We need to find the Earth twin. So we haven't done that yet. So far, we're only finding the Earth cousins. So out of the Earth cousins, if you want to know which are the favorites, I mean, there's about 6 of them. Some of them are called the TRAPPIST-1 planets. Those are kind of very popular. There's a few others. Their exact names escape me right now, but they have like letter and number combinations. But I could dig up like the 6 favorites for you that are being studied right now.
Noted. A lot of millionaires, billionaires watch this show, so they'll be ready to fund these missions. Let's start wrapping up. Before we move into the closing questions, I would love to know what masterpiece you've built with the Lego and what do you think I've built?
Okay. Wow. Well, first of all, when I build Lego, I always think about like there's sort of 2 options. There's 2 types of people in the world usually. Like one would build just something very regular and stable. And someone else may build some very crazy structures that are like barely stable, which is, the creativity versus the just sort of very ordered thinking. So I purposely built something that was like in between those to sort of highlight where I try to land whenever I do things. So yeah, it's not really meant to be anything. It's kind of very ordered, as you see, but it's not like a perfect rectangle and has a couple of interesting things. So it was sort of more capturing the philosophy of research and strategy.
It looks great. Definitely very structured, very functional, unlike mine, which can't even stand. What shapes do these look like to you?
I mean, if I had to guess, honestly, it almost looks like an animal of some kind.
Which one?
Well, I wanted to say a dinosaur because I was thinking about dinosaurs during our conversation. The question is, would dinosaurs ever become intelligent? Or were they so dominant and they've mastered their environment, there's no need to? And, we came around because the dinosaurs got extinct. Like a major catastrophe for some creatures actually opened up new possibility, right? So I've been thinking about dinosaurs, so that was why that was on my mind. An intelligent life form that's not human. But maybe you had something else in your mind.
I thought about dinosaurs as well and built it. That's
this one?
Yeah, I agree with you. What about the other one?
It reminds me more of a robot. Like, for whatever reason, we have these people, right? There's like a big push for humanoid robots. I mean, they don't need to be humanoid. There's a lot of robots that can still be functional. So I'll go for what's been on my mind of like, where we're evolving to. These humanoid robots, we don't need to be humanoid, but it's something that's big on people's mind, not to scale the dinosaur. And this one, I'm not sure, actually. But I really like your color choice. I love the blues and grays.
Robots and dinosaurs, there is some poetry there. I'm sure we'll find it.
Yeah.
Final questions. What are some books, movies, role models that have strongly influenced you in your life?
Well, I've read a lot of books, and I can't say that any have really influenced me for sure. But one of my favorite books ever is called The Giver.
Yeah,
I'm
but
not
Louis
sure.
Lowry.
And the book I came across because my children were in middle school a long time ago, and it was like assigned reading, and it looked like an easy read. You know, it's a pretty thin book, and it's written for middle school. And I just was so entranced by this book because, not to give any spoilers, but everyone should read it no matter your age. It's, about this society, but you can't tell if it's what's the word? There's like good versus bad. It's like, utopia or dystopia.
Yeah.
And so you don't really know which one it is actually. And I think it really is because a lot of us, like being on our phones or not paying attention, or just, you can easily fill up your time with TikTok. My kids now are grown up. One of them's turning 20. He's tried to ban me from TikTok because it's so brain rot. But, you can't really ban your parents from stuff. So, oh well. But I'm just saying, we don't really, we're often not thinking, right? And in this book, everyone's kind of marching along, not necessarily thinking. And it was a real wake-up call to see that book. So I would definitely put that book in it. In terms of role models, I can't really say I had a specific role model, actually. I'll just give you one little personal thing that later in my life, Marie Curie became a role model, because most people don't, you don't really read the whole story, but she had a husband who died. And they actually think that he got radiation poisoning, and he got kind of confused and fell in front of the carriage. Well, when I was about the same age as her, actually, my first husband died. It's not like the type of long form we're going to go into tragedy, but I was like, it was just hard. And I had kids, and she had kids. I'm like, what other widowed single mother really made it in life? And it was amazing, right? Because that was Marie Curie. So there's a real plus for her. That was not the reason you expected necessarily. But I do want to say what's really important. It is important to have someone in your life at any age, right? But when I was a child, I did have my dad. And he was incredibly eccentric. He's not alive now. And I can say that because I know he would call me eccentric. So it's all good. You don't want to say something bad about someone if they can't defend themselves. But his crazy ideas and theories, many of them I do not agree with at all. I could give you one example. He loved me so much. It's so great to be loved, honestly. I hope everyone gets to be that adored. But he told me we were going to be reincarnated. And I know some people believe in reincarnation, so I don't want to rain on anyone's parade, but he loved me so much. He's like, we're going to come back together over and over again in different lives. We could be business partners or brothers but I had to, and he believed in UFOs, and he believed in so many things despite being an educated person. And I gave him my book, which explained why UFOs it explained why UFOs haven't visited Earth or how there's no real evidence for it. And then he gave me his book. I don't think he read the book I gave him, but I read his, and all it was very weak evidence that was overhyped, But anyway, what happened was, as a child, I had to go there and sort through these theories on my own, which ended up being so important for becoming a scientist. But more importantly, he really influenced me because he was a big believer in the power of positive thinking. To get a vision of your future success at some concrete level and hold on to that vision, and then to be open to possibilities that'll help you get there. And he literally taught that to me at a young age. And in terms of a mentor, and he implemented this himself, that was pretty much the most instrumental thing that happened to me.
I would like to go there. In your memoir, The Smallest Lights in the Universe, you write very beautifully about processing death and dealing with death. First of your father, loss of your father, and then of your first husband, Mike, as well. How do you view mortality and your own impending death now? What is your relationship with it for the rest of us who thankfully haven't had the opportunity to process it on such a profound level as you? What advice can you give us? What is the relationship? Are you afraid of it now? Are you numbed by it? Do you look forward to it? How do you view mortality?
Well, I'm not afraid of it for sure. But the thing that's important, the grief is its own separate thing. But let's say the lesson learned is to make time count. And I know that sounds very cheesy and everything, but it's how to have impact, how to have your life have meaning. And I'm not talking about blowing like all that time on TikTok. That's still okay, right? Like you have the time when you're unwinding and you want to have your brain not really working too hard. But the question is, what does it mean for you? How can you make a difference? Those things are much more intense for me now, right? Because when you're faced with death so closely, I had to watch my dad got sick and he died within 3 months. So he didn't have time to like do anything. He just had to wrap up and say goodbye. But for my first husband, he did have time. And I just sort of had to watch him, like some things he can't do. Like he can't watch his kids grow up. They're out of his control. But what could he do? What is left in his time? And we did do something for a few months. It was very astonishing. We went to all our friends and we were like a team together. And we're like, if you only had 1 year to live, what would you do? And we asked everyone, and their answers were sometimes quite surprising. One astronomer colleague was like, I would drop astronomy and become a naturopathic healer. And other people would say things you might expect, like, well, I'd work less and spend more time with our kids. Yeah. Now, the thing is, if you're sick and you make that list of things you want to do, if you're like terminally ill, you get too sick too fast. You don't have time to do those things. And what we learned through that summer of doing that with our friends and colleagues, well, it turns out if you're well and you haven't had death close, you don't bother. But so my lesson, what I could do was do those. Like, what can I do to make a difference? And sometimes I do on a daily, it's kind of sounding weird, but on a daily basis, I'm like, okay, I usually don't tell people this, but I'd be like, well, is going to this meeting going to get to my impactful thing? And then I don't go. And so I do really try to get that. And I really wish there was some way I could articulate this and package it up and give it to people to get at least a part of that. How can we make a difference? How can we be impactful to other people? How can we, for lack of a better way to say it, make the world somehow in our own way a better place? And are my actions that I'm doing on a daily basis directly related? And that was what like a good thing to come out of grief was. Very good.
It's a powerful message. And while we're talking about impact and meaning, then I have to ask you, what would you like your legacy to be? How do you want to be remembered?
How do I want to be remembered? Well, I want to be remembered as an explorer who inspired others to focus on their dream and achieve their goals. That's how I'd like to be remembered.
I think you've already achieved that legacy. You almost became a doctor because your father wanted you to become a doctor. But selfishly, I'm glad you pursue this line of work because the work you've done with exoplanets and the work you're still going to do with space exploration, searching for extraterrestrial life, it's so monumental. So I'm happy you didn't go to med school and you became the Indiana Jones of astronomy instead.
Thank you.
Final question. What is the meaning of life, Sara Seager?
Yeah, that is a tough one. What is the meaning of life? I don't know. Honestly, I don't have an answer to that. Sometimes I go between what is the meaning of life? We're just here like any other life form, and we're put on this earth just to reproduce and make more of ourselves. That's what all the other life is here to do. And other times I hope we can aspire to reach higher than that. I hope that there is some ulterior meaning to life, but I haven't found it yet.
Well, keep me posted. You have my email if you find it.
Okay.
Professor, if people want to connect with you, if they want to find out more about you, your work, or you read your books, what is the best way to find you or your work?
People can go to my website, saraseager.com. That's just so old-fashioned. I don't have TikTok yet. I'm working on that. You can find me on Facebook and Instagram and all the apps.
That is the place to find you. Professor, this has been an honor for me. Thank you so much for such a fantastic conversation.
It's been my pleasure.